Hey, welcome back folks. Gary Simmons here for the Game Institute, and this is lesson 26 of the Dead Earth game development series, where we're going to take a slight detour away from developing our zombie states, and we're going to start to build a very basic first-person controller. And of course, over the lessons that come, we're going to flesh that out into something much more functional. But all we need for now is a basic first-person controller in the scene so that we can test that the player and the player's flashlight does register as a zombie threat, because we've written a lot of code to do with those visual threats and we haven't really tested any of it yet. And of course, once we've got a first-person controller in the scene, that will also help us developing the zombie's other states in future lessons, such as giving her something to attack and also making sure that she takes damage correctly when we shoot her and ultimately goes into a rag doll if we kill her. And later on you'll see we're also going to create a reanimation system where if a zombie is ragdolled, it can also get back up again if it hasn't been completely killed. So the first person controller that we're going to develop in this lesson and possibly the next is going to be a pretty basic controller to begin with, and in the future as we need more functionality we will add it. Now, if you've got Unity's standard assets imported into your project, and if you look in your standard assets folder, you can see that there is a characters folder, and in that characters folder there is a first person character folder, and in that folder there is a prefabs folder. And in there, as part of the standard assets, there is the FPS Controller, a fully functional, ready to go first person controller for use in your game. Now, if you're not seeing the characters folder in your standard assets folder, or if you haven't imported the standard assets at all, then you can go to the assets menu and you can go to the import package submenu and you can choose to import characters. But you don't have to do that because we are going to build our first person controller from scratch. I don't want to use the built-in Unity first person controller and all the scripts it contains. While it's very useful, if I do that, then in future lessons you're going to see me diving into Unity's FPS controller code, ripping out bits here, putting in more bits there, and if we don't understand the code fully, that's going to be complicated to follow. I think for educational purposes we should create our first person controller from scratch, and then you're going to understand every line of that code, even if it initially ends up being very similar to the code that Unity provides us with. So that's what we're going to do. So in order to start building our first person controller rig, we're going to have to add a new game object to the scene that will be the parent of that controller. So I'm going to go to the game object menu and I'm going to choose create empty. I'm then going to call that FPS Controller Rig. Now the reason I call it a rig is, although it will start off quite simple, in the end there are going to be many game objects as part of this rig. There's going to be the first person arms, there's going to be our camera, and there's going to be all of the various weapons that our animation system for our arms is going to need to interact with. So we have a game object in the scene. I'm just going to hold Control and Shift, just click on the square to make sure I snap it to the ground, just so I can see that I'm working with it and it's not hidden underneath the ground. So the next thing I'm going to do is I'm going to make sure that I set the layer of this object to player and the tag of this object to player also. We also want to check the physics manager to make sure that once we put a collider on this object that it doesn't fall through the floor. We need it to be collidable with all of the default geometry. So let me go to the edit menu, the project settings menu, and call up the physics menu. In the collision matrix in the physics inspector, we want to make sure that we have our player set to be collidable with the default layer, the transparent effects layer, the ignore raycast layer, and the water layer. Our player is already set to collide with some objects already, such as our AI trigger layer, and we absolutely want that to be the case, because if our player wasn't on the AI trigger layer, then it wouldn't register with Jill's trigger when our player entered it, and Jill wouldn't be able to see us. In my collision matrix, I've also currently got my player set to be collidable with the AI body part layer. Well, we have no AI body parts in our scene yet. That's going to be the layer that all of Jill's individual ragdoll colliders are going to be on a little further down the road. But either way, we don't want the player to be collidable with this layer anyway. So we just want it to be collidable with the basic geometry and with the AI trigger layer. Also make sure that in your game object, which I've called navigation example geometry, which contains all of our scene, that you have that set to the default layer as well. The only reason I mention this is because when I was doing a bit of prep work for this lesson, I noticed that somehow I'd accidentally set all of the geometry in the level to the AI entity layer, which of course is not at all what we want. So just make sure that all of those game objects and all of their child objects are set to be on the default layer. Going back to our FPS controller rig, we now have to add a very special type of built-in Unity component called the character controller. The character controller is a very special type of physics object. You can think of it as being like a capsule collider that acts like a kinematic rigid body. It isn't influenced by itself by gravity, it doesn't interact with forces and things like that. In a way, it has its own built-in physics system that handles sliding it along walls when we walk into walls instead of bouncing off of them like other physics objects would do. It handles sliding our capsule collider up slopes and also limiting the steepness of the slope that the character can walk up. And even better, it even handles moving our collider up steps, assuming the steps are within the height threshold that we set. So let's add one of these character controllers now. So with my FPS Controller Rig Game object selected, in its inspector I'm going to click the Add Component and I'm going to type CHR, and there you can see at the top of the list the character controller component. When I've added it, you can see the component has its own little inspector. Let's talk about what some of these settings do. The first is the slope limit. What we're saying here is that our character controller is allowed to navigate up any slopes that are less than or equal to 45 degrees in their incline. The step offset allows us to specify the height of steps that our character controller should be allowed to climb up. Here we're saying 0.3 meters. Next we have the skin width property. This allows us to dictate how much our capsule collider is allowed to slightly penetrate other objects in the scene. If this is 0, then there won't be any penetration, but you can often get a lot of jittering. So it's best to have a little bit of penetration that allows the collision system built into the character controller to resolve itself more smoothly. 0.08 is a good default, I'd leave it alone, but if you do alter the default radius of the character controller, the Unity documentation suggests that this should be set to around about 10% of your radius. Next up we have the minimum move distance, which I've always found I can set to 0, so I'm going to do that now. The minimum move distance is a way to resolve other types of jittering that might happen if your character is up against a wall, for example, and it's just constantly moving into that wall because the gap is very tiny between the collider and the wall, and therefore when you try to move it forward it kind of hits it, bounces off a little bit, and it's constantly sort of vibrating, but I haven't really noticed that, so I'm going to leave it at 0. I've had no problems with it. Next up we have the radius and the center and the height of the capsule collider that's used by the character controller. Well, we can't see it at the moment, so let's go down and have a look at what we've got. Now at the moment, because I've snapped the center of the object to the floor, our capsule is kind of not really aligned, so I want to get it roughly lined up with Jill so I can just see the sort of basic height. I should probably go to ISO mode for this, just to make sure I've got the capsule lined up with the floor as best as possible. Now it doesn't matter if we've got it lined up exactly, because even if we start this thing up in the air, by the time we've added our first person controller script, it's going to fall under gravity and land on the floor anyway. Okay, so the next thing I'm going to do is I'm going to set the height of our capsule collider to 1.8 meters, which I think is about the average human height, and I'm probably going to reduce the radius to about 0.3, maybe 0.4. And I'll need to move it down again just to make sure that the bottom of our capsule is on the floor. Okay, let me go back to perspective mode. Okay, so we have our basic capsule shape in the scene, and in a minute we're going to add a camera on the top of this rig that's going to be approximately at the zombie's head height. We want to be roughly the same size as our adult zombies. If we look at the character controller in the Unity documentation scripting reference, we can see all of those properties that we set in the inspector are also available via script, radius, height, etc. Also, some really cool properties such as is grounded, which would tell us when the capsule collider is in contact with the ground. If this is false, then it means obviously it's currently falling or jumping up in the air. We also have things such as the velocity that would tell us the velocity that our character is moving at. But to use the character controller, it's really simple. We just use the move function. When we use the move function, we just pass it a 3D vector describing the direction and magnitude at which we would like to move. Like I said, the character controller has a built-in physics system. It's not like other physics objects, which handles collisions and their responses in a way that is much more natural to a first-person shooter game. A real physics object, for example, when it hits a wall, would just bounce off that wall. But that would be hideous. If you were playing a first-person shooter game and when you ran into a wall you bounced off, it would be really annoying. What actually happens is when you run into a wall at an angle, you kind of stick to the wall and then you slide along it. And of course, we also want our capsule collider to slide along the ground and up slopes as well. So when we move our capsule collider using its move function, what's happening is its own little physics engine is operating on the colliders in the scene. But while the character controller isn't a traditional physics object that interacts with forces and gravity, it is a physics object in such that all of the collisions and the triggers and all those sorts of things still work just like a regular collider. Now later on, we're going to add a first-person shooter controller script that we're going to write that is going to talk to this character controller and tell it where to move, when to jump, and all those sorts of things. So the character controller is just the basic motor, the basic physics object that handles collisions in the correct way, but we still need to create a script that's going to drive it around. So the next thing we want to add to our rig is a child game object which will contain the actual camera. We definitely don't want the camera to be on this object as well, because when the player moves the mouse left and right, we're going to have our capsule collider rotating on the spot like so, and that's cool. That means if we have a camera on this object, the camera will also rotate left and right as well, like we would expect. However, we want to be able to rotate the camera up and down independent of this capsule collider, which we can do if it's on a child object. If we didn't do that, then when we looked up in the air, then we would be rotating the entire capsule collider around, and that would look kind of dumb. I don't know about you, but when I look down at the floor in real life, my legs don't rotate out behind me. Well, they do sometimes, but let's not get into that. Okay, so I'm going to add a child game object to our FPS controller rig by right-clicking on the game object and choosing Create Empty. Of course, because we've created an empty game object in this way, it's going to automatically be at the collider's position. We probably don't want it to be. We want it to be offset from the center of the collider. Otherwise, it's going to be like the head is in the middle of our body. So I'm going to move it up to about 0.6 for now, see what that looks like if I select both of those objects. Yeah, it's probably about right, roughly in line with the zombie's head. And I'm going to rename this game object in the hierarchy FPS Camera. And then I'm going to make sure that this is also assigned to the player layer. And then I'm going to add a component, and I'm going to add a new camera to this game object. We want this to be our new main camera. So I'm going to disable the camera that we already have in the scene. We no longer want that. We were using that to act like a tracking camera for Jill, but now we want to control the camera ourselves. I also want to change the sky that's going to be used by our first person camera, because at the moment it's rendering the Unity default skybox and there's nothing scary about that at all, is there? So I'm going to set the clear flags of this camera to solid color. I'm going to set that color to maybe not totally black, maybe like a kind of just off black with a bit of blue in it, something like that. Later on we'll mess around with the lighting a little bit and create a much more atmospheric scene, but I'm going to wait until we have our flashlight in the scene to do that. Next up, I'm going to make sure that this camera is tagged the main camera, okay, so that Unity knows that whenever any script asks for the main camera, this is the camera that it will return. Next up, I'm going to set the rendering path from its default, which is using player settings, which I think is forward rendering by default, to deferred rendering. And the reason I'm going to do that is that even though we're not using the standard shader on any of our scene, because this is a legacy Unity 4 level that we're dealing with here, and I haven't really thought it necessary to go around and change all the materials over, as this is just a test environment. You'll notice that we do still get kind of glimmering when we walk around the level. There's see these little white spots on these telephone wires, and you'll notice if you walk around the level you see quite a bit of this. If you change it to Unity's new deferred lighting mode, that will go away a great deal. Of course the light's too bright now, so what we'll do just to make it a bit more atmospheric is we will go up to our navigation example geometry game object. We will select that directional light and we'll turn it down to something a little more atmospheric, a little more dark. I think we'll also pull up the lighting tab, and we'll also make sure that we turn down ambient lighting, which is pretty bright as well. Yeah, I think the sky's a bit bright now. I think it probably could be almost totally black. So I'm going to select my camera again. I'm going to bring that color down to black, I think. There you go. That's looking a little bit better, isn't it? Okay, so we have our controller, but at the moment it's not going to do anything. If I press play, like I said, this isn't a traditional physics object. It won't fall under gravity. We can't move it around because we have no keyboard input or anything like that. So what we're going to do is we're going to write the script now that is going to be the engine that will drive that character controller around. So in order to do that, we need to create a new script. So I'm going to go to the project window. I'm going to draw down into my scripts folder, and I'm not going to go into the AI folder this time, but I'm going to create a new folder in my scripts folder, and I'm going to call this FPS Controller. And then I'm going to draw down into that folder and create a new C# script, which I'm going to call FPS Controller. Same name that Unity uses for its own standard assets script, but Unity's is within the standard assets namespace, whereas ours is not. Then what I'm going to do is I'm going to drag my first person controller script onto our FPS controller rig. We're now ready to start writing the script and get it doing something meaningful. Actually, I think what I'm going to do is I am going to move our controller out of the way for the time being so that it's behind Zombie Jill, because I don't want Zombie Jill like attacking us and running at us and all that sort of stuff, because we're not ready to deal with that quite yet. So I'll move it over there. Yeah, looks about right. We can't get away from Jill at the moment, so I definitely don't want to just running around. And also, Jill doesn't know what to do when she gets to us yet, because we haven't written the attack state. So we'll just have Jill kind of vanishing into us, intersecting our collider. So let's now open up that script in MonoDevelop and let's be about it, folks. So, as we usually do, just to uncomplicate things, to start with, I'm going to delete the boilerplate stuff, the update and the start function. And I'm also going to add the require component attribute above our FPS controller class, so that if we do drag this script onto a game object that doesn't have a character controller on it, the character controller will be forcefully added. I should mention actually before going on that this script is going to use the mouse look script from the standard assets characters pack. So if you haven't imported the characters package yet, make sure you go to the assets menu, import package, and choose to import the characters. And I think the mouse look script also uses the cross-platform input, so you may need to import that as well if it's not automatically brought in with the characters package. Okay, so going back. So the next thing I'm going to do is I'm going to create an enumeration that will describe the various different states that our FPS controller is in. Now this isn't going to so much be used by this particular script, it's just going to be set by this script, but other scripts that we generate down the line are going to need to know, for example, whether the controller is currently walking, running, landing, falling, etc. So I call this enumeration player move status, and you can see I have not moving, walking, running, not grounded, in other words in the air, and landing, which means we were in the air but now we've just made contact with the ground. So now let's think about some of the inspector variables that we're going to need so that we can configure how our FPS controller behaves. Well, the first is going to be a private float that I want to serialize in the inspector, and I call this walk speed. This is simply how fast we're going to move our controller around when we are in walking mode. Now in Dead Earth that's going to be when we're moving forward with either the WASD or the cursor keys, but we're not holding down the left shift. In our game, we're going to hold down the left shift key to activate run mode. So I'm just going to set this to 1 by default. So as you would expect, we're also going to need a very similar variable to describe the speed at which we would like our controller to move when it is running. In other words, when we are moving the controller with the left shift key held down. And I'm going to set this to 4.5 by default. And of course, we're going to be able to tweak these in the inspector to get the feel exactly how we want it. Next up, I want to set the jump speed, how quickly we jump up. And I'm going to set this to 7.5. Once again, it's an inspector variable. It's serialized so we can tweak this within the editor once we have our controller working. Now one of the things that we're going to have to counteract when we have a controller such as this is it's going to want to have a downforce that keeps it stuck to the ground when it's not supposed to be jumping, because our controller is going to fall under gravity. And what you'll see is often we get a falling sensation when we're just walking down steps. Instead of walking from one step to the next, we tend to fall from one step to the next. It makes the controller feel a bit floaty. It can also activate the kind of the landing state where the controller thinks it was falling and now it's just landed, and we don't want a landing sound effect playing as we walk down every step. So when we're not in the air, we want to have a force that's pushing down on our controller all the time, keeping it pushed into the ground. And of course, when we walk down a step, that's going to forcefully push it down onto the next step without it floating down, just using gravity as the only downforce. So I'm going to call this my stick to ground force, which I'm going to set to 5. By default, it's a private float, once again serializable so we can adjust it in the inspector, but I find this works pretty well. Next up, when our controller is in the air, we want it to be affected by gravity, and we know that we can access the physics settings of Unity to set the gravity of the physics system, and we can also read that value back. So while our character controller itself is not affected by gravity, in our FPS controller script we can read back what the gravity setting is of the physics system and then apply that gravity to our controller to move it down when it's in the air. In other words, when it's not grounded. But what you often find in a game is that you don't really want the player to fall down at the standard gravity rate that other objects are moving. Generally, you want a jump response to be a little more immediate, and it might not be particularly realistic, but it does provide better gameplay, and because a lot of games do this, I think it's just what we're used to now in games. So what we're going to do is also add a gravity multiplier, so that via the inspector, if the standard physics that's set by the physics system isn't enough, we can multiply it by a certain value to make it more intense, and then that gravity multiplier will be multiplied by the system gravity before it's applied to our character controller to have a stronger gravity force that applies just to our character controller. So once again, this is a private float, it's serialized, and I call it gravity multiplier, and I set it to 2.5 by default, which basically means 2.5 times the standard gravity is what we're going to push our player down at when he's falling off of a ledge or something like that. That works quite nice for me. Now, like I said, we're going to be using the Unity standard asset script called mouse look. Now, the mouse look script is a very simple script that is in the Unity standard assets.characters.firstperson namespace, and in the case of moving the mouse left or right, it will rotate the parent transform, in other words the transform of our character controller. But in the case of Y movement of the mouse, pushing it forward and back, it will rotate the child object, in other words our camera object, around its x-axis. So in other words, if I go back to the editor, this will rotate our camera up and down when we move the mouse forward and back, but it will rotate our capsule collider left and right when we move the mouse left and right. But of course, because our camera is a child of the parent rig, it will also rotate left and right with its parent. So that's exactly what we need. And it also has several variables so that we can set the sensitivity, so that via the inspector, if we don't like the way that mouse movement maps to rotational speed, we can adjust that. And we can also set the minimum and maximum extents that the camera is allowed to look up and down. And you can see here by default it's set to -90 and +90. In other words, we've got 180 degrees of vertical rotation. We can look right up in the sky and right down, but we wouldn't be able to look down so far that we started looking behind us through our legs. And you can see it also has a smooth property which allows us to activate smoothing based on the smooth time. And we've done lots of smoothing in our lessons. It's as you would expect. It just takes the mouse movement, which could be quite erratic, and smooths it slightly so that the rotation doesn't become too erratic and make us all feel motion sick. And you'll see that when we set this up in a minute, we call its init function, and we have to pass in the parent transform of the character controller and also the child transform that contains the actual camera. And that's because, of course, it needs to be able to rotate both of these things. It needs to rotate the parent object in response to a yaw, or in other words, horizontal movement of the mouse, and it needs to be able to rotate just the camera on its own, up and down, in response to forward and backward mouse movement. And the code's very simple. Check it out. It's nothing that we haven't done before. So the nice thing about this class is it totally takes care of reading the mouse X and Y axis and turning that into mouse movement and restraining it to sensible first-person shooter character controller defaults. So going back to our FPS controller, we're going to need to create a member of this type as well. So as you can see, it's a bit of a mouthful. I create a private variable of type Unity standard assets.characters.firstperson.mouselook, and I call this mouselook, like so. So now let's create our private variables block. One of the first things we're going to need is access to the actual camera. As you're going to see later on, we're going to add some head bobbing motion to this camera. So we're going to need to grab a reference to it so we can alter its position, and also so that we can read its position at scene startup. This doesn't need to be serialized, of course. We're going to do the hooking up of this reference in the start function. So we just create a private variable of type camera and set it to null by default. Next up, we're also going to need a boolean that's going to keep track of when the jump button is pressed. And the reason we need to do this is because our character controller is a physics object, which means when we move it, we also want to move it in the fixed update, not the regular frame update. However, the input system works in the regular update, so while it's fine to apply movement to our character controller in the fixed update, because generally when we're doing this, keys are being held down and can safely be read in the fixed update. In the case of a button press, where we generally just want to have it register the frame that the key is first depressed, if we are running at a frame rate of 2 frames per physics update, then we could have a situation where the button press is registered in 1 frame and then another frame activates after that before a physics update is executed, where that status is set back back to 0. So we just need to make sure that we always poll the button pressing in the update function, so that in our fixed update function, which might not be executing anywhere near as regular, that we record that it definitely has been pressed since the last fixed update, even if the previous frame that just executed didn't find that that button was pressed anymore. This will make more sense when we see the fixed update and the update functions. Okay, so next up, every fixed update, we're going to be querying the horizontal and vertical axes of the input manager, describing whether we should move horizontally, vertically, or in the case where they're both set, both. So what we're going to do is we're going to allocate a new class variable of type vector2 that we can use to store the result of that input as a 2D vector. So the x component of this vector will describe a -1 to +1 range value that we read back from the horizontal axis of the input system. And of course the y component of this vector will be used to store the -1 to +1 range value that we read back from the vertical axis of the input system. And of course, once we have this vector, it indirectly describes the direction that we wish to move in the world. If both the x and the y components are set, it means we wish to move diagonally. So what we have to do then is get these values and map them into some meaningful world units that can then be passed in to the character controller to move it. And when we map the input vector into that movement vector, we're going to store that in this vector 3 here called move direction. This is going to be the vector that we're going to actually pass into the character controller's move function. It's going to describe the actual direction and the magnitude that we wish to move the character controller this fixed update. Next up, we're going to need to know when the player has landed on the ground. Ultimately, we're going to be adding sound effects when the player lands on the ground, such as the boots hitting the floor. So we know already that our character controller has an is grounded Boolean property, so we can always find out whether the character controller is currently on the ground. But in order to figure out whether it's just landed, we need to also record what it was previously. In other words, if in a previous fixed update it wasn't grounded, but now it is grounded, we know it's just landed. So we need to add a Boolean so that we can keep track from frame to frame whether it was grounded, and then of course in the next frame we can check previously grounded to see if it was grounded in the frame before, and if it was, and of course the two booleans are different, then we know that we've landed. Next up, we're going to create two booleans that will just keep track of whether we're either in walking mode or running mode, and I call this is walking. It's set to true by default, meaning we're not running initially. And also another boolean called is jumping, which just keeps track whether we're currently in a jump cycle. If we're currently jumping, we don't want to allow the player to jump again, because if you're already in midair, you've got nothing to jump off of. Next up, I'm going to create a timer called our falling timer. And this falling timer is going to be incremented by delta time for each update that our controller is in the air. And the reason that we do this is because sometimes we may not want to activate a landing animation if we've only fallen a short amount of time. And I found in Dead Earth that if we've been falling for less than half a second, for example, then don't bother really registering it as a landing. Just ignore it. So whenever we're in the air, we will increment this timer, and whenever we land, we will set it back to 0, so that the entire time that we're in the air, this timer is going to be climbing up, and then we finally find that we've made contact with the ground. We can check the timer, we can say if it's past this certain threshold, then play the landing sound, otherwise don't play the landing sound or the landing sequence. You don't want this landing sequence playing if all you've done is fallen off a brick on the floor or something like that. So that's what that's for. Of course, we're also going to need a reference to the character controller so that we can talk to it, find out whether it's grounded from frame to frame, and of course call its move function in our fixed update function so we can cause this thing to move around the world. And we also created that enumeration called player move status. So I'm also going to create a private variable of type player move status, which I call movement status, and of course by default this is going to be set to not moving, and this is always going to be updated in our update function to reflect the current status of this FPS controller. And you'll see later on down the line other scripts are going to inquire about this status and use that in other ways. So now let's create some public properties so other scripts can get access to things such as our movement status. So I create a public property called movement status, returns a player movement status type enumeration, just returns our movement status variable. I also create a public float property called walk speed, just returns our internal walk speed. and a public float property called runSpeed, which once again just returns our runSpeed private variable. Okay, now let's get started on our start function. First thing we're going to do in that function is we're going to get a reference to the character controller that is on this game object and cache it in our character controller private variable. We're also going to grab a reference to the camera. Now, I don't do a get component here, I just use the camera class's main property, and this will search the scene for the camera that has been tagged with that main camera tag, which you will remember we have already done. So that's just a little shorthand way of getting that. Next up, I'm going to set the movement status to not moving, although let's be honest, that's unnecessary, isn't it? Because I set it up here in the initializer. But I'll set it down here anyway, what the hell. And I'm going to also reset our falling timer to 0 here as well. Also not necessary as I do it up here, but I just like to do things, especially with timers, I like to reset. I like to see them being reset in the start function for some reason. And then I'm going to call the initiation function of that mouseLook class from Unity Standard Assets, passing in our transform, which remember is the transform of our character controller, this thing here, and also passing in as the second parameter the transform of the camera itself, which remember is this thing here, the child object. And of course we've already discussed the mouseLook script needs both of those transforms so it can rotate them independently. Okay, so now our start function is done. Let's work on our fixed update function. First thing we're going to do in the fixed update function is we're going to query the input manager, and we're going to use the get axis function to get both the horizontal axis and the vertical axis. And by default, these axes are mapped to the WASD keys and the cursor keys. So providing you haven't messed around with the input manager in this project, these should already be set up and ready to go. And they should return values in the -1 to +1 range. And you can see I store these in these floats called horizontal and vertical. I then set a boolean called was walking to the current state of is walking, because we're going to change the state of is walking in a moment. Now we're not going to see that being used in our first implementation, but I may use it later in the fixed update function when I add some other things such as the field of view kick, which I haven't decided whether I'm going to add yet. But just in case we do need to know if we were walking and now we're no longer walking, I'm going to record that in this boolean here. Next up, we need to find if we're currently walking, and we do that by using the input manager's get key function to see if the left shift is being held down. And you can see I pass into the get key function keycode.left shift, and if the left shift is being held, then this will return true. And you can see that I flip the result using the not operation. Notice I use the get key function here, not the get key down function, which is why it doesn't represent a problem using this in the fixed update function. If we were using get key down, it would only be registered in the one frame that it was pressed, and we might have multiple frames between a fixed update, and therefore when we got into the fixed update function we might actually miss the press. It might already be reset back to false. But get key will stay true the entire time the key is being held down, so we have no such problems using it here. So let's calculate the speed that we're moving our controller at, and you can see if we're walking, then we'll set this to our walk speed. Otherwise we'll set it to our run speed, and remember walk speed and run speed are set up here and are set to 1 and 4.5 respectively by default. So now let's take our two floats, our horizontal and our vertical float, and let's store them in our input vector. So I create a new vector2 passing in horizontal and vertical as the x and y components respectively. Okay, next up we're going to check the magnitude of this input vector. And if it's greater than 1, we're going to normalize it, because this is ultimately going to be multiplied by our speed and used to move the actual character controller through the world. So if this is greater than 1, then we're going to end up moving it at a faster speed than our walk speed or our run speed. So we need to make sure that the vector we're going to use is unit length. Notice I use squared magnitude here and not magnitude, which you might think would give the wrong result. But remember, if the length of the vector is less than 1, then so too will the squared magnitude. And if it is 1, then of course 1 times 1 is 1. So still works. Okay, so next up we're going to take this input vector and we're going to calculate a 3D vector that describes the direction we wish to move. I call this desired move, and I do it by taking the forward movement and multiplying that by our character controller's forward vector. And we add on to that our character controller's right vector multiplied by the amount of horizontal movement that we wish to do. Remember, the horizontal movement in this case is not rotating, it's strafing left and right. So we do wish to move it along its right vector, either positively or negatively. So we now have the vector that describes the direction we would like to move. but it isn't necessarily the direction we're going to move. Imagine, for example, we're standing on a 45-degree incline. Pushing forward, if we actually moved ourselves forward, we would actually move right into the geometry, right into the slope, such that we were intersecting it. Of course, what we want to do is take the direction that we wish to move and then project that onto the polygon that we're standing on. In this case, we would be flattening our forward vector such that it was now planar on the slope surface. So it's now describing the direction that we wish to move as being up that 45-degree incline. So we're going to use one of the physics functions, in this case a sphere cast, where we pass in the position of our controller. We're also going to pass in the radius, and we're saying we want to cast a ray in the world down direction. Okay, we want to find the point directly underneath our feet. And of course, with these physics functions, if you pass in a raycast hit struct, it's going to fill that out and give us lots of juicy information about what we hit and the normal of the surface that we hit, and that's actually the more important thing. So we pass in that with the out parameter modifier, and the amount we wish to cast the ray down is simply half the height of our character controller. Remember, the character controller's position is at the capsule center point. So we're going to cast down character controller height divided by 2. And the final parameter is the layer mask that we wish to use to tell the function which geometric layers should be sensitive to this sphere cast. I set 1, which basically means all layers, okay? And if the physics sphere cast function does return true, then it means we are standing on a surface, in which case we wish to project our desired movement vector onto that plane. So that, like I said, in the case of we're standing on a slope, we're going to generate a vector not that describes a movement into the slope, but instead a movement that is planar to the surface moving up the slope. Unfortunately, Unity's Vector3 class has this really useful project on plane function, which is used precisely for this purpose. As the first parameter, we pass in the vector that we would like to project or flatten onto the plane, and as the second parameter we pass in the plane normal, which is the normal of the surface that we're stood on in this case. So that will take our movement vector, it will flatten it such that it describes a direction that's planar to the surface, and then we normalize the result. So we now have a nice normalized vector describing accurately the direction we wish to move our character controller. But of course, we don't just want to pass in the desired movement vector into the character controller's move function, because it's unit length. Our character controller would never be allowed to move at a speed greater than 1, and it would completely ignore our speed variable up here, which is either set to the walk speed or run speed. So of course, all we have to do is multiply this desired movement vector by our speed to make it the length we want, and store the result in our move direction vector, like so. So now our movement direction vector accurately describes the amount that we would like to move both vertically and horizontally. And when I say vertically, I'm actually talking movement along the z-axis in the world, okay? So forward-backward movement, not up and down movement. But we're not quite ready to pass this vector into the move function of the character controller yet, because we need to find out whether we're going up or down. We need to find out whether the character is jumping or not. So the next thing we'll do is we'll contact our character controller and we'll check what its isGrounded boolean is set to. So here you can see if character controller dot is grounded, then we're going to step into this little block of code here, which will only be executed if our character controller is physically in contact with the ground. And then what we'll do is we'll set this Y component to the negative of our stick to ground force. Remember, this is the force that is supposed to be always pushing our character controller down so that it's stuck to the ground when it's in normal mode. And that's why we only do this if we're grounded, not if we're in the air. So now we need to check if the jump button has been pressed. Now you're going to see in a moment that the jump button boolean is going to be set in the update function, whereas we're currently working in the fixed update function. So don't worry about how this gets set to true for now. Just know that some frame update has happened between now and our previous fixed update that has registered that the user has pressed the jump key, and it has set this boolean to true. Remember, we only do this test if we're grounded, because we can't jump if we're already in the air. And if the jump button has been pressed, then we're going to essentially undo this stick to ground force and a lot more besides by adding our jump speed to it, which will give it positive movement up the world Y axis. But of course, if the jump button wasn't pressed and we're just walking around the level normally, the Y component of our move direction vector is going to be negative along its Y axis, keeping it grounded. So once we've processed the jump, we should set the jump button pressed boolean back to false, so that in another update function it could be set back to true again. And then we're going to set our isJumpIn boolean to true, and that's pretty much all we have to do in the jumping case. You see here, I've put a to do here, and I'm going to do that a little bit in this code. And next up, we set our isJumping boolean to true, so any other inquiring object or even other parts of this script will know when we're currently in a jumping state. You can see afterwards I also put a comment in there saying to do play jumping sound. I'm not going to deal with sounds at the moment, but this is exactly where we would register that the sound of the player's boots leaving the ground would need to be played. And later on, because I've put to do here in capitals, the colon, we can find all of these to do's very easily in MonoDevelop. Okay then, so if we're not grounded, then it must mean we're in the air and we're falling. So we simply add on to our movement direction vector what the current gravity force is. Remember, we can get this by using the physics class's gravity property multiplied by our gravity multiplier multiplied by time.fixed delta time. We now have our move direction vector accurately describing the direction that we wish to move our controller, even if in the case of we're not grounded, that is a downward motion of us falling under gravity. All we have to do now is pass it in to our character controller moves function. We pass in our move direction scaled by time.fixed delta time. Our fixed update function for the time being is done, my friends. Let's now work on the update function. The first thing we're going to do in the update function is once again contact our character controller to see if it's grounded. If it is grounded, we're going to make sure that our falling timer is always set to 0. But if it's not grounded, then we need to increment that falling timer. We're keeping track of the amount of time that our character has been in the air. Next up, we're going to use that mouse look object that was one of the standard asset scripts, and in particular, its look rotation function. This function is passed the transform of our parent object, the character controller, and the transform of our camera, and it will take care of reading the horizontal and vertical mouse movement and either rotating our character controller left or right in the case of horizontal mouse movement, or rotating our camera up and down in the case of vertical mouse movement. Notice, however, that I do this little check before. I just check that the time scale isn't set to 0, such as if, for example, we'd paused the system and we'd set time.timescale to 0, because the look rotation function will generate a load of nan errors if you do that. Okay, so we just want to make sure if the game's paused or you've set timescale to 0 that we don't still call this function. When this function returns, our character controller and our camera will be oriented in the correct direction. Next up, we want to see if the jump button has been pressed, and if it hasn't, we want to see if it is being pressed. So you can see we say if the jump button isn't currently pressed, then we're going to set the jump button pressed to the result of the input class's getButtonDown function passing in the name of the button we'd like to query as jump. Once again, if you haven't messed around with the default settings of this project, then the input manager should still be set up to have this jump button defined. And if we go to the project settings and call up the input manager, we can see that jump is set to be either joystick button 3 or the space bar. So if the jump button has been pressed for just this frame, then the getButtonDown function of the input class will return true. And that's why we need to store that result so that we have access to it in the fixed update function, just in case multiple frames per fixed update had happened. Okay, so the next thing we want to do is we want to see if the player was in the air but is now grounded, because that gives us an ideal place to play a landing sound or invoke some kind of landing animation. So I do this by doing the following. I say if we weren't previously grounded and now the character controller is telling us it is grounded, then it means we have just landed. This is the first update that we have made contact with the floor. So in here we could play a landing sound effect, and ultimately we will. But I'm not going to focus on sounds in this lesson, okay? So we're just going to put the placeholder code and comments in there for that. But we may also invoke a landing animation, and we'll probably add a landing kind of head bob later on down the road as well. But I also said earlier on that I don't want this code block to be triggered prematurely if we've only fallen a very short distance. So what I do, because we're keeping track of the amount of time that we're not grounded, the amount of time that we're falling, I also say only step into this code if the falling timer is larger than half a second. And okay guys, feel free to shoot me. I've hard coded this value, but you could, of course, make this falling timer threshold an inspector variable. And you can see that inside this conditional, I have a comment that says play landing sound, where we will eventually do that. But either way, whether we're playing a landing sound effect or not, we've hit the ground. It's time to zero out any movement in the Y direction. Finally, we'll set is jumping to false. We're no longer jumping, we've just hit the ground. And we'll set our movement status to player move status landing. Otherwise, if we haven't just landed, then we need to check if we're not grounded, because if we're not grounded, then our status should be player move status not grounded instead. But if we haven't just landed and we're not in the air, then let's check if we're moving by checking the squared magnitude of our velocity, and if that's smaller than 0.01, then we set our status to player move status not moving. Otherwise, we are moving, but we need to set our status to either walking or running. So you can see I say else. If we're walking, then set our status to player move status is walking. Otherwise, set it to player move status running, and I think that covers all the bases. Finally, we want to record in the previously grounded boolean the current is grounded boolean of our character controller, so that next frame we will be able to remember whether we were grounded this frame. And I think that's pretty much it for now. We're going to add some more stuff later, but I just noticed there was a spelling mistake there, probably quite a few. Okay, so let's save that off, check I haven't got any errors. No errors. Okay, so let's press play now and prepare to have your world set alight by an incredibly realistic controller. So there you go, there's our walk speed, but you can see we haven't implemented any head bob or anything like that, and there's our run speed. But it does work as I move the mouse around. You know, it does look up and down, it looks left and right. Oh, there's Zombie Jill, she's walking. Notice Zombie Jill, let's check if she sees me as a threat when I run past her. Oh yes, look at that, she saw me. She's coming after me. I need to shake her off, so see if I can shake her off. Okay, I've shaken her off, I think. You can see there she is. She's at the very last place she saw me, look, when I dodged round the corner. Whoa, now she's coming at me again. Dun, 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 dun. Now, you can see there that what's happened there. Why can't she see me? I'll tell you why she can't see me. If I move in front of her, what's happened is Zombie Jill has got far too much of a narrow view cone. So let's adjust that now before we do anything else. Because I think we set Jill's view cone to about 60 degrees, which is only 30 degrees either side. And of course, that is ridiculous because in the real life, we've probably got something more like 180 degree vision, haven't we? I mean, if I hold my hand out from my ear, I can still see it. In fact, it might even be more than that. I can see at least probably 100 degrees either side. Maybe I'm talking nonsense, but anyway, it's a hell of a lot more than 30 degrees either side, and that's why she couldn't see us then. So selecting Zombie Jill and her AI entity game object, let's put her sight value, not sight value, that's how far she can see. It's the field of view, isn't it? I'm going to set that all the way up to say something like, do you know what, I'll set it to 180. And we should now see that even when I dodge out of the way, if I'm at an extreme angle to her, hello, oops, she's seen me. Okay, so I'm going to duck around the corner. And you'll notice when I duck around the corner, what she does is she can only go to the last place she saw me. She's given up on me entirely. Where is she? The hell is she? Oh my god. What's she doing around there? Okay, here she comes. I think she might have... There you go, look, there she is. But you can see now she found me, even though I was at quite an extreme angle to her. Let's try that again. Where's she gone? Oh, I'm behind her. So about, yeah, there you go. She was able to get me around about when I stepped in her vision. So that's cool. Okay, so as per usual, time has run away with us much quicker than we expected. So we are going to pick this up in the next video where we're going to continue to work on our first-person controller. We're going to add a head bob system to make the camera kind of bob up and down as we're walking, make the whole walking and running motion feel a little bit more real and organic. We're also going to put in place some of the code that we'll use later to make sure that our controller tells whatever sound system we end up making when and where to play the footstep sounds, which of course need to be spaced differently depending on whether we're walking or we're running. We're also going to add the flashlight to the scene, so you're going to see how we set up the player's flashlight, how we set up its trigger, and we're going to make sure that Jill reacts to that flashlight threat properly. And we're also going to make a little tweak to our alerted state, because when I was running the demo just now, I noticed that when I dodged out of the way of Jill and she ran to the last place that she saw me, she dropped into the alerted state, and that was fine. But what she does when she's at the last known location of the player but can no longer see the player is she just kind of stands there in the alerted state and she doesn't seek left or right. Because I thought that would look good, but now having seen it, I'm not so sure. Well, in fact, I am sure. I'm sure it doesn't look good. So what I'm going to do, I think, is when she gets to the last known location of the player but she's lost sight of the player as a visual threat, is I'm going to have her just randomly seeking left and right. And that way, even if you think you're outside of a view cone, she could just randomly turn around and reacquire you more easily. And I think that's what was missing from Jill's behaviour just now. Okay, so thanks for listening, guys. I will see you in the next lesson. Bye bye for now.